So it's the first time I give a talk with a beer, so thank you for that. My name is Hadrien Commenges, so I'm a geographer and an associate professor at the University of Paris 1. And my presentation is about quantitative toponymy. So the main title, where is Eugène Pottier, is a teaser, and you will understand later this title. So I will begin with 2 or 3 examples of studies in quantitative toponymy. You may know that one by Stefana. So it's a study of the location of specific endings of German place names based on regular expressions and coordinate extraction from the Geonames database. And the result, I will show it quickly, of this study is to show the overrepresentation of specific endings of German place names. So for example, here in the north east of Germany, we have many place names ending by O. Here is another example, endings by Rod, out here, or Ba in the southwest. So this is a recent example of quantitative toponymy. Here is another example. So it's also based on the Geonames database, and with some regular expressions and detection of specific endings of place names with river name. Here Salmon extract all the municipalities with those endings with the main French rivers. And if you plot the result of this query, you get the rivers. So you may think that it's useless, but if you think that it's useless, you are wrong, because in many cases the things, the names last longer than the things. And if there is a big global warming and the rivers disappear, the names stay here. So the names are very often the track we have of former things. And you can find many studies of that kind. Here, for example, it's a study about the location of heathland distribution. Heath means, so I just searched for it, it's Heide in German, or Bruyère in Français. So it's a specific vegetation. And here the authors search these specific toponyms, and then they compare the present land use, it's in Galicia in Spain, the present land use and the heath distribution with the former land use with the tracks by the toponyms. So it is very useful to have toponyms because the things disappear and the names don't. So here is my story. Where is Eugène Pottier? So it begins with this question: who is Eugène Pottier? So he's a very famous socialist revolutionary, and he is the composer of the song the International. And he is one of the most famous communards, meaning the revolutionaries of the Commune de Paris in 1871. So my guess is that these characteristics, he's left-wing socialist legend, and he is a musician. My guess is that these 2 characteristics will give him a specific location in the space of names. So if my question is, where is Eugène Pottier? So I have 3 answers here. You may answer he is in hell or in heaven if you are a left-wing or a right-wing believer. You may answer, if you are an agnostic, he is exactly here in the sector number 95 of the cemetery Le Père-Lachaise. But what if you are a quantitative toponymist, and what if you are looking for this name in the space of names and not in the space, the geographical space? Here you can see 4 streets in the south of Lyon. The street Eugène Pottier, street Rouget de Lille, who is the composer of the national anthem La Marseillaise. Here the street Maurice Thorez, who is one of the main leader of the Communist Party. And here the street Martyrs du 8 février 1962. So this is the date of huge killing of Algerian demonstrators. Yeah. So we have here 3 typical left-wing names and 2 typical musicians' names. And my guess is that Eugène Pottier will have a very specific place in the space of the names of all the French streets. So my initial data set is the OSM dataset of the roads, the French roads, in the whole country. So this is about 6 million features. From these 6 million features, I select only the primary, secondary, and tertiary and residential features in the OSM dataset. That is about 2 million features. And then I select only the urban areas, and so that is about 1 million features. So this is my first selection, only by feature class, and this is the final data set with this urban areas selection. And this selection is important because in between you have many roads with no names. This is not streets, this is roads with no names. So this is my data set, 1 million features, 1 million streets or streets parts. The first step of my study is a textual processing. So I have to remove the stop words that has no meaning. I have to remove the feature class, like rue, boulevard, avenue. And here, for example, with these 3 names, rue Eugène Pottier, promenade Maurice Thorez, quai des Martyrs du 8 février, I remove these parts here and I have only the streets names. And then I have a little problem here. Some streets are a combination of feature types. So for example, the bridge street, I can't deal with that. It disappears of my dataset because I can't do, I mean, the cleaning is endless, so I have to put some limits. But I get the main, I mean, this is residual, I think. So this is the first step, the textual processing. And then I have a specific problem. So this is an example given by Michael Goodchild in a conference given in Paris last December. And so he said that the problems with place names is that it is very often a point pattern. It is very often a point pattern, and it's easy to manipulate if it is a point pattern. But in my case, it is not a point pattern. So here, if you look for the Mississippi River in Google Maps, you will have a point. But if you look for the Mississippi River in the OSM website, you will have the whole line. And in my case, I have lines and not point pattern. So how can I deal with that? In the first place, I have spatial lines from the OSM database. The classical way to convert a set of spatial lines into a network, the transportation approach, would be to consider that crossroads are vertices linked by streets, meaning that at the end of this conversion, you have a set of vertices that are crossroads and a set of edges or links that are streets. But I can't deal with that kind of data structure. To answer to my question, I have to do the exact opposite. Meaning that, so this is what I call here the toponymist conversion. For me, the streets are vertices in the network, and the crossroads are edges, are links between those vertices. So this conversion, I mean, I didn't invented it, but it's not very common because the classical way is to do that kind of network conversion. So I will create a network with all the streets names, and so it is an undirected and valuated network. This network has about 200,000 vertices, meaning distinct street names. It has about 700,000 edges between those names. It has one giant component, which is nearly the whole network, and 4,000 tiny components, which are mainly topological errors in the database. And here you can see the top 10 by degree, by vertex degree, the top 10 streets names in France. And no surprise here, Église, church in the first place, Grande République, Général de Gaulle, Jean Jaurès. So these are the main streets names in the country. But that's not what I'm looking for. I'm looking for a way to quantify preferential links between names. And to do that, I create something which is a nearly chi-squared matrix, or in the network literature you will call it a quasi-modularity matrix. And here the computation is quite easy. So it is the idea that the expected weight between two vertices depends on the weight of both vertices, and it is normalized by the total weight of the matrix. So the only difference between my equations and the chi-squared or modularity computation is that the diagonal of my weights matrix is empty, and this is why here in the denominator I have those terms. And at the end I have an expected weight between two vertices, and I can compare the expected weight with the observed weight with something which is something like Pearson residuals. So this is the observed weight between two vertices, the expected weight between the same vertices, and here the square root of the expected weight. And this is a measure of the preferential links between my vertices, between my street names. And I will use this measure to plot the preferential links between names. So here is the answer to my question. Where is Eugène Pottier? He is here between his friends from the Commune de Paris. So here you can see the main left-wing legends of the Commune de Paris. Louise Michel, for example, Jules Vallès, the name Commune de 1871, Commune de Paris here. And so this plot is in the center. I put the name I want to explore, and here the distance between one name and the center is inversely proportional to my Pearson residual. So here we have a very straight relationship between those names. And here, for example, Rouget de Lille, which is the composer of the national anthem, we have a preferential link, but not as strong as this one, for example. And I can do this for all the names I have in my data. So, for example, for Louise Michel, which is who is another very famous communard left-wing legend, I have the same names here: Jules Vallès, Eugène Pottier, and also I have some important revolutionary women. For example, here, Olympe de Gouges, Simone de Beauvoir, Marie Curie. So this is a specificity of Louise Michel. And I can explore clusters of names and demonstrate that each name has a specific location in the space of names. Another example here, if I plot Mozart, I will get, as you can see, a plot of musicians, because we have neighborhoods with musicians' names. So what can I do with that? I can use that as the track of an old land use, meaning if I have a cluster of former left-wing legends, I suppose that it is a former left-wing neighborhood, and in big cities it is what we call the red belts, in Paris or in Lyon, the red belts of the city. And so I can compare these names, these neighborhoods, with the present land use. So here it is not a land use, it is the social characteristics of the population. And for example,